right, so in this particular problem, we have a block of mass m, which is 4 kilograms here. It's this initial at rest, and it's released from the top. The ramp is rough, so the coefficient of the ramp is given here as 0.24, and then this is the length of the ramp is 15 meters, okay? The angle theta is given in the diagram as 30 degrees. So let's go ahead and crack out A, B, and C. All right, but before you do these types of problem, I highly encourage you to draw out the free body diagrams for the forces acting on the block or box, whatever it is that you're assessing. So here, the block arrow this came up, that is my weight, which is my F of G, and F of G by definition is just mass times gravity. But then F of G has components for these types of ramp problem because we treat the surface of the ramp as our x-axis, so the x-axis is tilted. So therefore, F of G has F of Gy, which lies on the y-axis. So as you tilt your x-axis, your y-axis has to tilt with it as well. So this is F of Gy. And then here, this component that just came up, this is F of Gx. I know it's F of Gx because if you watch my cursor, if I just drew that line there, it parallels the surface of the ramp, which we call x. So hence, this is F of Gx, okay? The angle given here in the diagram for the incline is 30 degrees, so this theta is also the same theta. So it's important that you place theta here, that's between F of Gy and F of G. So it's this angle that I'm tracing back and forth, that is the same as the angle of the ramp due to geometry. All right, so cosine of theta, by definition, is adjacent over hypotenuse. We know our adjacent in this case is F of Gy. We know our hypotenuse is F of G because this is a right triangle. Therefore, the leg facing opposite of the right angle is always your hypotenuse. So F of G in this case lies in between the x and y axis that's been tilted, okay? So cosine of theta is equal to adjacent over hypotenuse. And then to solve for F of Gy, we simply multiply both sides by F of G. Therefore, F of Gy is simply F of G times cosine theta. But we know that we can substitute out F of G. F of G is simply mass times gravity, okay? So we say F of Gy is mg cosine theta. And this particular expression is pretty solid for these types of ramp problem. Once you do a few, F of Gy according to this angle reference is always going to be mg cosine theta. So hopefully after a few problems you can stop deriving stuff and just use it. All right. F of Gx though is your opposite of this angle, so therefore because the opposite in geometry we use sine. Sine by definition is opposite over hypotenuse. So if you're looking from this theta reference, this is your opposite leg, which is F of Gx, and then your hypotenuse is F of G. So therefore we say sine of theta is opposite, which is F of Gx, over hypotenuse, which is F of G. And if we solve for F of Gx, we need to multiply both sides by F of G. Okay, so therefore F of G sine theta is F of Gx, but F of G once again can be broken down to mg times sine theta. So just as F of Gy, after a while, F of Gx, you can stop doing this step because it will always turn out to be mg sine theta according to this angle that's referencing the angle of the ramp. Okay, unless they do anything funky, that will always be mg sine theta, right? But as the box naturally wants to slide down the ramp for this problem, it tells us that there is a coefficient of friction. This is the coefficient of friction, not the force of kinetic friction. So differentiate between mu k and f of k. But I know that if the box wants to slide down the ramp, there's an f of k opposing it for this problem. So therefore, f of k needs to parallel the surface, but it's going to point upslope instead of downslope. Okay. So the box wants to go downslope. So therefore, f of k acts against it for this problem. So therefore, it has to point upslope. So to find f of k though, for part A, it's not too bad. F of k is simply mu k times f of n. We know what mu k is, we don't know what f of n is, so therefore we need to look on the y-axis. Again, the tilt axis has been tilted. This vertical component along the y-axis is f of gx. This red arrow is the force exerted by the surface, aka the ramp, onto the block. Okay, so this contact force is called f of n. And if you notice here in the y direction, there are only two arrows. There is an F of Gy pointing down due to the weight of the block, but then the surface pushes back up on the block with equal in magnitude, which is called F of n, the normal force. So we can substitute out F of n for F of Gy for this problem because there are only two arrows along the y-axis, suggesting that Fn is indeed the same magnitude as F of Gy. So I substitute out Fn for F of Gy. But we already know down here from our work earlier that F of Gy is simply mg cosine theta. So I can substitute out f of g y for f of g cosine theta in the next line. But then I know f of g is mg. So as you can see here, these types of problem requires you to just do a bunch of little substitution based on the expression you're trying to find and based on how detailed you're expanding your function out to be. Okay. So once I expand f of g to mg, I know all these values. Mu k is 0.24, mass is 4, g here is 9.8, and then cosine of 30 because the angle is given here in the diagram is 30. If you punch on your calculator, you should get a value of 8.15 or about 8.15. All right, it asks for magnitude, so I'll leave the answer without the direction, so that is going to be my answer. Part B asks you to find the magnitude of the acceleration. Well, it's not too bad. The box will naturally want to slide down the slope. Well, what's causing it to slide down slope is f of gx, because f of gx parallel the surface of the ramp, but it's also pointing down the ramp. But this is what's causing the box to slide down. However, as it slides down, there's f of k opposing it, and f of k in this case, once again, is pointing upslope. So here for the x direction, I only have two forces. So if you look at the horizontal or the x direction that's been tilted here, I see an arrow pointing down slope, I see an arrow pointing up slope, and those are the only two arrows that you need to incorporate into Newton's second law for the x direction. But we know f of gx is mg sine theta from our work down here earlier from the bottom left where I'm circling back and forth with my cursor. So once again, f of gx will always be mg sine theta unless the angle is somehow messed with you. All right. F of k though is mu k f of n. Once again, if you pay attention to my work, it's from here. F of k is mu k f of n. But we already derived what f of k is in terms of mu k and all that stuff. But I'm going to pretend like I don't know part A, just in case you were not asked to do part A and just asked to do part B directly. Okay. So therefore, f of k can be substituted for mu k f of n. And then f of n can be substituted out for this problem, f of g y. Because once again, there's a f of g y pointing down, f of n pointing up. Those two must equal in magnitude. For f of gy though, we can substitute it out for mg cosine theta. And then here you notice m cancels out on both sides because there's an m on each of these terms. So if you simplify it, you can also factor out g. This is g sine theta. This is mu k g cosine theta. So here I've chosen to factor out g. You don't have to. You can leave it as is and just plug in values, okay? I'm just going to factor out g. This is an expression to find a for this problem. G times sine of theta minus mu k times cosine theta. Therefore, once you have all that, you can just plug it in. You know that g is 9.8, sine of the angle is 30, and then mu k is 0.24, and then cosine is also 30. So here, once again, you can plug in 9.8 here, but that's up to you. So if you plug in g's 9.8 in the front and you multiply by this whole quantity in the parentheses, you should get a value of 2.86 meters per second square. And it asks for a magnitude, so I'll leave my answer as is. Okay. Part C asks you to find the time that it takes to reach the bottom of the ramp. This one is pretty light work. To find the time it takes to reach the bottom of the ramp, I would just use my displacement function. I think this is the easiest way, but it's entirely up to you if you want to use a different approach. Here, VI is 0 because it says release from rest, so therefore I can get rid of VIT term because that's just going to be equal to 0. Delta x here I just replace with L because it says the length of the ramp. So instead, you can keep it as delta x, but the problem says L, so I'll just replace delta x with L. Okay, and then it's just 1/2 AT squared. But to solve for t squared, I need to multiply both sides by 2, divide both sides by a. So I did 2 steps in one there. So I moved the 2 up to the left, and then I moved the a down into the denominator because you're dividing. So it would be 2L divided by a, which is equal to t squared. Once we have this, L is 15. A, we just calculated in part B, which is 2.86. So again, A is over here. It's 2.86. So I substitute in L for 15, A for 2.86, and that's equal to t squared. If you simplify this on your calculator on the left side, it equals to about 10.49. But this is t squared, so therefore to get t by itself, you need the radical both sides. So the square root of 10.49 would give me a value of about 3.24 seconds. Okay, so that would take about 3.24 seconds to cover the distance of 15 meters down the ramp. All right, other than that, that is it for this particular video. All right, I hope that helps. Stay nerdy, don't be whack.